Hello and welcome to this Global Azure virtual talk on Azure Cognitive Services, AI and the rise of the machines. I'm Bill Ayres. I've set of contact details here if you'd like to get in touch with me. I won't bore you with the bio and get straight into the topic. I've got a picture of what's called a brainbow. So it's a lovely word, brainbow, and it's what neuroscientists can use, one of their tools, to visualize individual neurons in a brain, in this case a mouse brain, but it could also be other types of brain. And they use fluorescent proteins to identify the individual neurons and the connections between them. And they can actually see the wiring inside a brain. So in a very simple brain, like some creature that has just a dozen or so neurons, you can actually sort of see the wiring or the circuit diagram and figure out how it works. And this is one of the many techniques that neuroscientists can see how neurons work, and it's been understood for over 100 years. And so networks have always been of interest to AI researchers. So when people in the 1960s, early 60s, late 50s wanted to build artificial intelligence, that's the model they used. And so they built something that looked a bit like a network of neurons. So this device, that's the picture on the right, is a perceptron. It's actually a sort of an electromechanical contraption. There's a set of photocells and you can present an image to it. This is from the 1960s. And there's a kind of a patchwork of wiring, and then there's at the far right you can see an array of motorized potentiometers that adjust the weightings for all the different inputs and then sum those and give an output. And the idea there is that you can present an image to the set of inputs, and then using machine learning, using various techniques to train the model and adjust all these weights using things like backpropagation to feed back the error function, you can automatically adjust these weights and teach the perceptron to recognize different images. Now, there was a tremendous amount of excitement over this technique, and when people saw they were able to identify very simple objects or shapes with it. And so there was a huge amount of interest in research, and funding was made available. And this is all happening about 60 years ago. And as often happens with technology, it was overhyped. Everybody got too excited. The military got involved and thought they could identify Russian planes and build robots to shoot them down and things. And of course, it was really unrealistic because the amount of computing power available was quite small. And I can remember a few dire predictions. A number of people looked at this. One was, I remember actually seeing a talk by Professor Sir James Lighthill, who would wave his hands in a rather spectacular, and I thought at the time thinking rather silly fashion, and saying, trying to explain the combinatorial explosion that happens when you try and apply these techniques to more complex problems. And he said, you'll never be able to do things like machine translation or speech recognition. So there was a realization for mathematical reasons that very simple perceptron single layer neural network model just wasn't going to work or deliver anything like the capabilities that had been promised. And so there was this all the funding for research dried up, and AI researchers called this the first AI winter, where you couldn't really get money for any kind of project, and all interest evaporated. Now it kind of flared up again in the early 90s, late 80s and early 90s. And there was another wave of interest in artificial intelligence, mainly around a different technique called expert systems, where you'd get somebody who was knowledgeable in some particular domain, like medicine, for example, and try and build up a set of diagnostic rules, and then that would be encapsulated into a computer program. And there were expert systems that were designed to be easy to train and capture that knowledge. That didn't really work either. I remember because I was involved in that, and it didn't really pan out. Primarily it was a problem of scale, that you couldn't scale that process. It was too expensive to build these models, and they weren't that good when you'd built them. And now here we are in 2020. It's the next big thing again, artificial intelligence, and we've gone back to the machine learning ideas that we originally had in the 1960s with the perceptron, but somewhat more complex, and we call that deep learning. And this time it does look as though it's actually working, and we can demonstrate that we can do useful things with the technology. So what changed? Well, it's still the neural network, but we have multi-layer neural networks where there's a hidden layer, and that increases the number of possibilities and overcomes that limitation that was correctly identified with the single layer neural network that was originally used. And you don't just have one layer, you have 50 or more of these hidden layers. In the case of some of the models we're going to look at, there may well be 150 plus of these hidden layers, and that allows the models to be much more complex, but it also means that they're to some extent opaque, in that you can't see what all these hidden layers are doing, and so it's not obvious. So it's a bit like going back to the brains, where you can look at the wiring of a very simple brain and work out how it works, but something more complex, like say a human brain, is really too complicated just by looking at the wiring to work out what it's doing. And it's similar with these multi-layer neural networks. It's not obvious how they work. And that's one of the criticisms of them, but they do work. And why do they work now when they didn't work 60 years ago? Well, we've now got much more computing power, we've got faster computers, and we can also rent 100,000 computers for half an hour very easily using the cloud. So we've got this huge resource available to us that we can share, and so that works very well. And we've also got the internet, which has a huge amount of data that we can use as training data for these models. So the machine learning scales very well. We can deploy all these machines to learn against huge arrays of training data and train these models, and that approach has been very successful. Let's see just how successful. Over the last 10 years we've gone from things like speech recognition and image classification have gone from 60% or 30% of no practical use to us. Things like speech recognition and handwriting recognition used to be a joke, and yet now within the last couple of years we've got to the point where they are better than 5% error rates, and that 5% level is significant because 5% is the error rate of a human being. So suddenly, once you get below 5%, you've got a machine learning algorithm that can go through 100,000 photographs, doesn't get bored, doesn't get tired, and tag them, for example, and that can read through an entire book and translate it into another language. Good enough for all kinds of practical applications and business applications. So this has really changed things fundamentally, that we can now do things with machine learning. Now, any technology is only useful if it's easy to use and easy to apply. So let's look at some of the things that Microsoft's been doing in Azure to make it easy to use these machine learning models. And I'm not talking about doing what the data scientists do, which is build the models, but we're going to look at some pre-built models in Azure. So if I go to Azure Cognitive Services, I think you can work out how to get there. It's easy enough to find. And there's a range of pre-built models. These are pre-built machine learning models that, for example, will do things like a content moderator for offensive content, lots of language, text analytics, language understanding, which looks at the words and their intent, speech itself, so speech to text, text to speech, and speech translation. All these are pre-built models. You can feed them data, and you don't have to train them. You don't have to build them. You just use the API endpoint, and it gives you a response. We'll look at, for example, computer vision would be an easy one to just see an example of. And there's a demo here. So if I choose, say, this picture of somebody on a skateboard, there's a REST API that you can call. You give it the image, and it'll then analyze it in Azure and come back with a prediction of, well, I can see a skateboard, but it also it's not 100% accurate. It'll say, well, it might be snowboarding, some sort of sports equipment. It sees a person. So it's analyzed the picture, and somebody has already trained this model, and they keep updating them and improving them, but they've fed them hundreds of thousands, perhaps millions of images that they have labeled, and they've trained the model to identify these things, and it works surprisingly well. And so you can feed it pretty much a random image, and it'll have a pretty good guess at what's in there. Now, what I want to build is a tool to identify particular species of butterfly. Now, that's clearly beyond something like this, which has a few hundred everyday objects that it'll identify. It might identify a butterfly. It certainly won't identify individual species. So for that, you need to use a more custom model. And there is a tool called Custom Vision. So we go back to Vision. That was computer vision. There's another one called Custom Vision. It's still a pre-built model, but it's one that we get to train ourselves. So we feed it some images. So here, identifying empty and full fridges, for example, you can train the model with particular images that you're interested in. And then when you've built that model, you can either use it from a REST endpoint like the other services, or you can deploy that model onto a device or in a web browser. Let's look at Custom Vision. I've already set one up here, which is called Butterflies. Let me go back here. So I've got a Custom Vision account set up, application set up in my Azure subscription. And if I want to create a new project, I just say new project, and I'd say butterflies. I've done it already, and give it a description. I can choose the resource that I've set up in Azure, and then there are a few different types of projects. We'll look at classification. There's also one called object detection, so I can teach it to, say, identify butterflies in a picture and draw a box around them, and teach it to identify or detect the objects. But classification is for distinguishing between different labels. So I will choose the single tag per image, and I'm going to choose the general domain, and then I won't create this project because I've already done one, but give it a set of images and tag them and say these are all this type of butterfly and these are some other type of butterfly, and it will use that as data to do machine learning. And this process is called supervised learning because we are specifying what the classes are. So I've already created one here. It's pretty easy to add more images. So what I need to do is I go to here, I say add images, and if I wanted to say add all these here, I'd say add those, and then I need to add a tag. So you can see I've already added this one, so I'd say the monarch tag in this case, and upload those files. So I already did that, and then the other thing I need to do is hit this train button, and I can run that through the training algorithm. Now already ran that once. It takes a couple of minutes to go through and train the model, and then we can test it. There's a quick test button here. I can say let me load up a file, and I've got another folder here of test images. So these are images that aren't part of the training data, and we can use that to see how accurate the model is. So I can feed it a peacock butterfly, and I see from the predictions that it is correctly predicted that that's a peacock. I've got about 20 images that I've just pulled in from Bing for each of these different butterfly species. Here's the red admiral. It successfully identifies a red admiral with 99.9% probability. And then if we give it another one, which is the painted lady, which is very similar actually to a red admiral. A lot of people get these two confused, but not our image classification algorithm. So really good. This is amazingly accurate for so little effort, and something that would have been unthinkable a few years ago to be able to do this. So very effective. Now, a word of caution: you can throw it a curveball and say, well, we'll send it a picture of Katarina Johnson-Thompson, and it says, oh, that must be is probably a peacock butterfly. And if I send it a picture of a Ferrari, then it's similarly confused. And the worrying thing is it's actually quite a high confidence as well that it's a peacock butterfly. The problem here is we've built a classifier that can distinguish different butterfly species. Doesn't know anything about cars and decathletes and other topics, so it's a very narrow field that we've trained it for. If we wanted to do this in practice, you'd have to be aware of that, and perhaps if it was important, you would give it lots of pictures that weren't butterflies, sort of negative samples, or you could sort of stack the models and have a first model that does object detection, and then when you've found a butterfly, then you feed it to the classifier. If you use this naively, then you can get very misleading result. When it gets it wrong, it can get it spectacularly wrong. So you do have to be a little bit careful. Now that's a general model. I can also use what's called the compact model. So when we did new project, you remember I selected general, but I can also select general compact. They're also different pre-built models, but they haven't been trained yet. So I can use what's called the general compact model, and that has the ability to export to some other platform. And there are different AI platforms. One of them is TensorFlow, and we'll have a look at that in a second. So when we've built one of these, and I've done the same thing, the training is exactly the same, and you go in and you normally we'd go to a prediction URL, which is a REST endpoint in Azure, but I can also go and say I want to export this model, and you get a slightly confusing set of choices here that sort of associates TensorFlow with Android. I'm not quite sure why, but if I click on TensorFlow, I can choose TensorFlow JS, and if I download that model, that will give me a zip file with a JSON file and a set of weightings, which is about 4 megabytes in size, which is the weightings of the different layers in our deep neural network. So let's have a look at that. So if I go to PowerShell and open Visual Studio Code, this is where I've previously downloaded this model to, and I have this on GitHub. If you're interested, you can go to the SP Doctor GitHub repository, which is, let me show you where that is. It's github.com/spdoctor, and in there it is called, where's it gone, repositories. TensorFlow JS is the repository that has this code in that we're looking at now. So this is the model under this folder butterflies. I've got a set of labels, so monarch, painted lady, peacock and red admiral, and this is the JSON file, which is a kind of a map of all the different layers, and then all the weights. It's a binary file. You're not really meant to look at those. There's nothing really that we can learn much from. It's just the output of that training process has now been condensed into this set of files. So I've got a a file butterflies.html, which will load up the TensorFlow and TFJS, TensorFlow.js and Converter JavaScript libraries. And then down here I'm going to load this butterflies.js that I've written, and what that does is it loads up the model. I've told it where that unpacked zip file is. It's going to take in that model. So this model was trained in Azure using the custom vision API, and then it loads that up, and then there's it loops around a loop where it captures the webcam and then attempts to look at the image in the webcam and applies the butterfly classifier to it. So I can run that by going back to here, and I've installed an HTTPS server, and I'm going to run that on port 3000. And then if I open the Chrome browser here at localhost 3000, so that's now loaded up that page. So what I've got, this is the list of the items that it took from that labels text file. So these are the labels that I applied to the training data, and this is a tensor, which is really just an array of the probabilities for those four. So they're jumping around at the moment because I'm not a butterfly, so I pretend to be a butterfly, it will get confused. At the moment it thinks I'm a peacock butterfly. It always seems to head for that one by default. But if we start showing it some actual pictures of butterflies, so I've got the I Spy Butterflies and Moths book here, and in fact on the cover it's got a peacock butterfly. You see it's identified that the tensor is, if it gets over 95%, it will show a picture below it. And if I then change to let's find one of the ones we built the classifier for, there's the Red Admiral. It's successfully identified that, and there's a peacock butterfly. Need a bit more light really. Sometimes it can even get it just from quite a detailed part of it, a bit blurred. So it gives you a bit of an inkling as to what the model might be looking for. In fact, if I go back here, I've got another little demonstration here that actually looks at the layers. So this is the same thing, but I can actually look at this is the different layers in the network, and you can actually look at, not that informative, but you can sort of get an indication of how it's the different hidden layers are doing different transformations and convolutions on the image, and layer upon layer of this. It's all beyond the scope of what we're talking about here, but eventually it will be identifying sections of the image or line detection and all kinds of things. That's really the skill of the designer of the model itself, but we don't have to worry about it. We can just use it. It's ready to use. We just need to train it, which is what we did in Azure. Okay, so as you can see, in practice it is surprisingly easy to build a classifier. We did it for butterflies, but there are lots of business applications of this kind of thing where you can fairly easily build something that's going to be very useful from a business perspective, and it's not something that's difficult to do. You don't have to hire a team of specialists to do it. You can get something working using these pre-built models. It's incredible. It's be difficult to imagine we would have been at this point 10 years ago. We should perhaps remember that these are very narrow machine learning models that we're building. It's not general intelligence, but they are very useful, and they do have some consequences. So you have to think a little bit about some of the ethical issues, particularly around, say, if you were to build, for example, human resources job candidate filtering system where you train the model to identify people who are likely to be good employees, it would be very easy to unintentionally build in all kinds of biases and discrimination into that kind of model, perhaps without realizing it. Where a human HR person would never dream of doing that because they'd know it was ethically wrong and probably illegal. The model might do it accidentally. So we have to be very careful about how we use these, because you can't really see how it's reaching its conclusions. There's also rather worryingly what's called an existential threat around artificial superintelligence, and that's the topic of this book by Nick Bostrom, which is a little bit worrying. There are a few people have talked about this, and there's a prediction that a lot of experts think that in the next 30 to 50 years, probably seems a long way off at the moment, but that there could well be a point where artificial general intelligence, we're nowhere near that at the moment, but it would take off very steeply. So whereas human intelligence, limited by the laws of evolution to very gradually improve human intelligence, machine intelligence, there's no such limitation, and it's not even limited by our own ability to build better computers, because presumably if the artificial intelligence was that good, it would be able to design better computers, and so the whole thing would take off. It's something we need to be thinking about now, even though the threat is probably in reality some way off. Now, it doesn't help that the popular press usually use a picture from the Terminator movies to illustrate this point, and much to the irritation of professional researchers in artificial intelligence. I don't think that's a very realistic danger of robots. I think it'll be something much more subtle. One of the examples is that somebody programs a machine to make as many paper clips as possible, and then it sees the humans as being an obstacle to achieving that objective, and it's clever enough, to outwit us. You can't just switch it off because it's too clever. So read that book if you want to be scared about all these possibilities. But in the meantime, we've got the opportunity to build some really nice business solutions without too much effort. So artificial intelligence and machine learning have definitely arrived. They are useful. We can apply them to real business problems. There are some ethical and other risks around it we need to be aware of, but it's a great opportunity to apply this technology without having to be an expert on machine learning. We can actually use these things now. So let's take advantage of it and build things and use these great cognitive services capabilities inside Azure. Hope that was interesting. Thanks very much for listening, and have a great time with the rest of the Azure Global Virtual.